All right, so we want to talk a little bit about vectors and kind of describe how to draw them and what they are, what they mean, that kind of thing. So when we talk about vectors, first off, we are talking about something that has magnitude and direction. So things like velocity or displacement, forces. These are all things that have magnitude associated with them and also a direction associated with them. So this is opposed to something like a speed that is scalar and only describes the magnitude of that property. Now vectors are drawn as an arrow, and the magnitude is represented by the length of the arrow. And really by definition, since it's an arrow, it shows the direction. So the direction is represented by the direction that the arrow is pointing. For this particular video, we are going to describe vectors using displacement. Just keep in mind that these same principles apply for anything that is represented by a vector. So here we have our coordinate system. We have our starting point. And let's just say that we are going to move 20 meters to the north. So 20 meters to the north, where's my pin? There we go, is our first vector coordinate. So the first thing that we have to decide is which way is north. Most of us are pretty familiar with maps, and most maps that we deal with use the coordinate system, or the top of the paper represents the north direction. So we're going to use that as our coordinate system. So we are going to define as the top of the paper, as we move towards the top of the paper, we're moving towards the north. We're just going to stay with that convention because it's something that we really like. You really could say that this is north, or this is north, or this is north. It doesn't really matter, as long as you're consistent in your references. So this is what we refer to as our coordinate system for this particular problem. And it's going to stay the same for our problem. If we get to a different problem and we want to redefine it, we can do that later. So this would make over here east, over here south, and over here west. So for our situation, we're moving 20 meters to the north. We would simply draw our arrow. We're going to start here. This is our origin. We're just going to define that as 0. We're going to draw our arrow so it is traveling to the north. So our vector is going to point towards the top of the paper. Now the other part of the vector is the magnitude, and so we want to define a scale for to represent our magnitude. So we're going to take our ruler. Where's my ruler? We'll take our ruler. We've got a really nice 10 centimeter distance there to the top. So let's just make our scale. Let's just say that our scale is 1 centimeter on our ruler is going to represent 2 meters on our vector. So when we draw our vector, we're going to draw it 10 centimeters long. So 20 meters, every 2 meters is 1 centimeter. So 20 divided by 2 is going to be 10. So we're just going to start here at 0. We're going to go up to 10. Okay, how do I see that? We're going up to 10 centimeters. So our vector is represented by 10 centimeters, which represents 20 meters to the north. Oops. There we go. So what if somebody wants to move 14 meters to the east? Let's just say that's our second vector. So we're going to start here again. East is this direction. Our scale is still 2 meters is equal to 1 centimeter. So if we have 14 meters, we need 7 centimeters. So we're going to take our ruler. We're going to draw a 7 centimeter vector. So 14 meters to the east is drawn to the east of our paper and represented by a 7 centimeter vector. Now we can make it a little more interesting. let's just say that we want to move 7 meters. Let's go southwest. All right, so we're going to start here again. Our scale is still 2 meters for every centimeter. So our scale is going to be 3.5 centimeters. Is going to represent 7 meters on our scale. And we are going to line that up halfway in between the south coordinate and the west coordinate. And we're going to draw our vector. So when we say southwest, we just mean exactly halfway in between south and west coordinates. So if we line up 3.5 centimeters, oops, there we go, exactly halfway in between that south and that west, that is our vector. Now notice up here when I was going in a straight line, we did not use the blocks as our scale. And the reason for that is as soon as you get into something that's not one single block, a block diagonal does not equal a block up and down or side to side. So we really don't want to use blocks as our scale, because when we start getting into angles, that's going to be really difficult to convert. Now I would like to point out that if we are moving in exactly a southwest direction, so this is our southwest direction, we can also label the angle at which we're traveling. Since west and south are 90 degrees to each other, halfway in between would be a 45-degree angle. So this angle right here is 45 degrees, and this angle right here is also 45 degrees. So we can also say that we are traveling in a direction that is 45 degrees west of south. So we're going to take our angle here and we're going to go 45 degrees to the west of our south coordinate. Now we can also say we are 45 degrees to the south of west. There's different ways that we can write that, and you'll hear it in several different directions. So we want to make sure that we can say 7 meters, 45 degrees south of west. So if we're going west, we're going to go 45 degrees to the south of that marker. Or we can say 7 meters, 45 degrees to the west of south. These are all the same things. Now we can also take that idea and we can apply it to something that's not exactly halfway in between. Let's say that we're going to move in a direction 18 meters in a direction that is, let's say 23 degrees north of west. All right. Okay, well, west is over here and north is up here. So our direction is sort of in the northwest direction, but not exactly. So we're going to take our protractor and we're going to line it up. We are north of west. So west is going to be our 0 line. And we're going to be 23 degrees north of west. So we're going to put a little dot right there. And then it's 18 meters. Our scale is still 2 meters. Oops, you can't see that down there. Our scale is still 2 meters equals 1 centimeter. So we're going to have 18 meters is going to be equal to 9 centimeters on our scale. So we're going to start at 0, line up our 0 point and our angle point. 9 centimeters is going to represent that 18 meters, and we are 23 degrees to the north of west. So let's do one more. Let's go 11 meters in a direction, 84 degrees south of east. Okay, here's south, down here, here's east over here. So we're going to go south of east. And we're going to go 84 degrees. So if we line up our protractor so that east is 0, we are going to go 84 degrees way over here south of east. Now this is 11 meters, and our scale is still 2 meters for every centimeter. So 11 divided by 2 is going to be 5.5. So 5.5 is right here. So this right here is 84 degrees. Now we could also call this 6 degrees to the east of south. It's going to be the same thing. All right, so our vectors then, vectors have magnitude and direction. They are represented by the length of the arrow, and the arrow itself is represented by a direction. And if it is not along one of your horizontal or vertical coordinate planes, then we have to measure those angles.